So, so what do we mean by 50% seed loading or 80% seed loading? This these words might sound a bit weird for you. In industries, the percentage seed loading during a typical crystal growth experiment will be roughly around 3 weight percentage. Yeah? So in order to understand what's mean by this percentage seed loading, we have to understand a bit about the given experimental conditions. So I'm going to repeat. I'm going to write the initial conditions. So we know the solubility of paracetamol at 20 degrees centigrade. 20 degrees centigrade is 108.78. So gram of paracetamol per kg of solvent, and added in the how much we added in the experiment. So we added, for the growth experiment, we added 76.048 gram of paracetamol in 750 ml of isopropanol. So these are your initial experimental conditions. So these are your initial experimental conditions. This is your solubility data that we take from literature. So if you need to, before before thinking about the percentage seed loading, the first job we should do is like we have to calculate the supersaturation ratio. What's that? And then we have to calculate the amount of mass that we can crystallize from this experiment. So if you want, we can call it as the theoretical amount of mass that we can crystallize. And always remember, whenever we are talking about the crystallization, it can be nucleation or crystal growth. We need to think about supersaturation and solubility. So keep these things always in your mind. So then you will solve this crystal growth problem or nucleation problem really easily. Yeah. So before trying to understand about seed loading, the first thing you should calculate is your supersaturation ratio, and then you should calculate the theoretical amount of mass that we can crystallize. If we have this value, then we can calculate something from based on the value about how much, like 50% seed loading. We can make a sense out of this terminology, like 50% seed loading, 10% seed loading, 3% seed loading. Everything will make sense only if you manage to calculate this value, how much mass that you can theoretically crystallize from that crystallizer, and how to calculate that. So we all know supersaturation ratio is C by C star. S is equal to C by C star. So the concentration, we know how much we added, 76.048 gram of paracetamol per 750 ml of isopropanol solution. So we have to calculate solubility, or we have to express solubility in the same unit, gram of paracetamol per 750 ml of IPA. So we have this value, but in a slightly different units. So, so C star at 20 degrees centigrade is 108 point, what's the value? 78 gram of paracetamol per kg of solvent. I think so far so good. So what we need to do is like, first let's convert this into grams per liter. So let's how to convert this one. So obviously we can convert directly into grams per 750 ml of 750 ml of solvent, but I'm going to show different units because in the exam I'm going to ask something like, okay, that's the solubility value, express the calculate the supersaturation ratio and express concentration in different units. So you should know how to calculate this one. So for the beginning, let's convert the solubility value gram per kg of solvent to gram of paracetamol per, let's begin with the gram of solvent. Let's go one by one, and then we have, let's convert this into, how do, what can we do, like maybe grams of paracetamol to per liter of solvent in this case is isopropanol IPA. So let's do one by one. So let's do this step. Let's call this step 1. So this is very easy. C star is equal to 108.78 divided by, you have kg of solvent, so 1 kg is equal to 1000 grams. So just divide by 1000, so that should give this units, gram of paracetamol divided by gram of solvent. So what this value will be, this will be equal to 0.10878 gram per gram of IPA and gram of paracetamol. So first part is done, and then now we have to convert gram of paracetamol per gram of IPA into gram of paracetamol per liter of your isopropanol solution. So to do that, or to, in order to convert mass to volume, so we need to convert mass to volume. So which means we need density. We know density is equal to mass by volume. So if you need to convert your gram mass, which is in gram, say let's say mass is expressed in gram, say volume is expressed in liters, and imagine we have the density value which is expressed in grams per liter, then we can calculate your volume. So volume will be nothing but mass divided by density of IPA. These are really basic, yeah. This it's too easy. So what's the density? Density of IPA is 786 grams per liter. So what does that mean? Like, you just put, if you don't know to, or if you don't feel confident with unit conversion, you can follow this simple rule. You have grams, you have liters. So just put, make a column. So what does this mean? 786 gram will give 1 liter. Or if you weigh, if you put 1 liter of isopropanol and then if you put it on the weigh balance, it will weigh 786 grams. So if you're, so what will, how much will be, so you already have gram of IPA here, so we need to convert this into liter of IPA. So 786 gram will weigh 1 liter. So how many gram, how many liters will be 1 gram, 1 gram of IPA? So just put x, all you need is to cross multiplication. So every time follow this simple rule, that will save your life. 786x is equal to 1 multiplied by 1. So x will be equal to 1 by 786. So x is equal to 0.001272 liters. These are really basics, but students do a lot of mistakes. It's not easy, yeah? So at least try to use pen and paper one time in the home after listening to this lecture, or during the lecture. Try to use the pen and paper and try to solve it by yourself. So now we can convert C star is equal to 10 gram of paracetamol how much is this value? 108, no, we already calculated 0.010, no, C star is equal to 0.10878 divided by gram of, this is gram of paracetamol divided by gram of IPA. So 1 gram of so 1 gram of IPA will be equal to how many liters? That will be equal to 0.001272 liters. So this should give you your solubility concentration. So that will be how, what's this value will be. Mm, Let me use my calculator. So what's this value? 0.10878 0.10878 divided by 0.001272. That will be equal to 85.518 gram of paracetamol per liter of IPA, isopropanol. So now we need to calculate the supersaturation ratio. S is equal to C by C star, where C is expressed in terms of gram of paracetamol per 750 ml of IPA. And this one should be C star must be expressed in the same units. So we have to convert this C star to gram of paracetamol per 750 ml of IPA. So how to do that? It's very simple. So just take this value. So 1 gram and then milliliters. We know 1 liter is equal to 1000 milliliters. So if you come back to this box, so 85.518 gram. So this is the solubility value in 1000 ml. 1000 ml of your isopropanol solution. So how much in 750 ml? So just put X, do the cross multiplication. So this is a simple rule. 750 multiplied by 85.518 is equal to 1000 multiplied by X. So therefore X will be equal to 750 multiplied by 85.518 divided by 1000. So how much this value will be equal to? I think I calculated this value already. So this value should be equal to 64.125 gram of paracetamol per 750 ml of isopropanol solution. Hope you all are following. So this is your solubility at 20 degrees centigrade. So this is your solubility at 20 degrees centigrade. So I think now we have the enough data to calculate the supersaturation ratio. So when this is initial condition, so initial experimental condition. So initial experimental condition, your supersaturation ratio is C by C star. So we added how many grams? 70, I forgot. Let me check. 76.048 gram of paracetamol. 76.048 grams of paracetamol per 750 ml of IPA. I know for chemical engineering students, this might look a bit slow, but believe me, you might do the same mistake. Yeah, so try to pay attention, and even if you do a small mistake, the whole answer will become wrong. So it's not a bad idea to do the calculations a bit slow. So C star will be equal to, just now we calculated, it's here, 64.125 64.125 gram of paracetamol per 750 ml IPA. So whatever the numbers that we are calculating, all these values are connected with the crystal growth experiment that we performed in the lab. So this is your initial supersaturation. This is your initial supersaturation. Supersaturation ratio, to be precise. And now Now we have C value, C star value, both in the same units. So now we can calculate the mass that we can crystallize. So you all remember this solubility plot. I plotted many times, like temperature, your C value here. So this is your C star, and then you add something amount up to this point. Say this is your 64.125 grams. Your solubility, say this is at 20 degrees centigrade, and just assume you added some point. This is your the actual mass which you added, 76.048 gram. Just assume that's the solubility somewhere at 30 degrees centigrade approximately. So what we are going to do is, like, we will heat the solution to 60 degrees centigrade, which, and then we are going to cool back the solution back to 20 degrees centigrade. So that time you might have created some supersaturation, and from this, just from this plot, you will know how much mass we can crystallize. That will be equal to how much you added minus your solubility. So the mass that we can crystallize is C minus C star. I said to you many times, the driving force for crystallization is supersaturation, not concentration gradient. Yeah? So if you don't have supersaturation, there is no crystallization. So you have to listen to part 1, part 1A, part 1B, part 1C in detail to understand how this solubility and supersaturation works, and how to create supersaturation, how to create the driving force that allows you to, that gives you the right condition in order to crystallize a compound. It can be through nucleation or it can be through growth. If you want to go for nucleation, you have to work at the limit of metastable zone width. If you just need the growth, then we have to work under the safe conditions. So so your the theoretical mass that you can crystallize will be equal to C minus C star. That's nothing but 76.048 minus 64.125. Oh, by the way, this supersaturation ratio, the answer will be around 1.18, approximately 1.2, but better use this value 1.18. That's your initial supersaturation. So this is your experimental condition for both of your experiments. And then for both of the experiments, the mass that we can crystallize is 76.048 minus 64.125. So how much will be, what will be the number? Check in the calculator. 76.048 minus 64.125, that will be equal to 11.923. So this is the mass of paracetamol that we can crystallize in 750 ml of IPA solution. In the exam, I might ask how much mass that you can crystallize from 1 liter of IPA solution. Then you have to convert. You have to convert this, like how to do that. Like say like a gram of paracetamol, and then say like 1000 ml, or just put milliliters of IPA. So in 750 milliliters, we can theoretically crystallize 11.923. So how much we can crystallize in 1000? So just put x, do the cross multiplication again. So 11.923 multiplied by 1000, that will be equal to 750 times multiplied by x. So x will be equal to 11.923 multiplied by 1000 divided by 750. So whatever the value we get, maybe I can calculate it right now. Divided by 750, that will be equal to 15.897 gram of paracetamol per liter of IPA. Many of the people who work in crystallization field, they use up to three how do you call, like three numbers after the decimal point. So try to stop here. Yeah, don't write some number like 15.9871234 until you finish your ink in the pen. Yeah, don't do that. so this is your solubility value as well. Sorry, your delta C. So I think we fairly covered some basics, like how to convert the units and how to play with the numbers based on the solubility data and based on your initial experimental conditions. So I think this is enough. And then, so before I said, in your final report, you have to make a plot of supersaturation versus time. Yeah? So since you started your experiment at 1.18, so this value, the first value will be 1.18 when time t equal to 0. Time t equal to 0 is here. Let's express time in minutes, and then it will grow slowly. Then it will come to the constant. So this, it will come constant when supersaturation ratio equals to 1. So that time, yes, C by C star, that will be equal to 1. So which means your C approached your solubility concentration. So which means there is no driving force. So you will get some trend like this for when you load with 50% seeds, and then you might get some trend like that. It might even reach 1 somewhere a bit early when we used 80% seeds. Or percentage seed loading is 50%, percentage seed loading is 80%. Something like that. So this is your 80% seed loading. I think I'm going a bit slow. Anyway, still we will finish this in time. And then I asked you to, in the final report, you should include another graph, which is delta C. That is the mass that you can crystallize. In this case, gram of paracetamol per 750 ml of IPA versus time and then what we get is like when we are going to plot, it's going to go something like here. So it will start from 0. What does that mean? When time t equal to 0, we crystallized 0 mass. But with time it will increase progressively, and then eventually it reaches some saturation point. So delta C is nothing but C minus C star. So it will reach, we already calculated this value. What's that value we calculated? Let's go back to this page. So that will be equal to 11.923. So you will reach this plateau when delta C is equal to 11.923 gram of paracetamol per 750 ml of IPA. Say if this is for your 50% seed loading, for the experiment that we did with 80% seed loading, this one will reach even faster this maximum point or the equilibrium stage. It's not even equilibrium, we can call it as a saturation because we are dealing with crystallization process. So this will be your 80% seed loading. This will be your 80% seed loading. So this is your 80% seed loading, and then This is your 50% seed. You might expect this trend. If this trend may not be true, so whatever you get, just plot it. So that's what we have to calculate. Yes, and then delta C. I already showed you how to calculate your Q value. And then what does, let's come back to this original statement, 50% seed loading and 80% seed loading. What do I mean by that? So 50% seed loading. 50% seed loading. So we know how much mass we can crystallize in our experiment, which is C minus C star. That's equal to, how much is that? 11.923. So gram of paracetamol per 750 ml of IPA. So 50% seed loading means just 50% of this, 50% of the theoretical mass that we can crystallize. Whatever the number we get, that will be the mass of the seeds that we are going to add into the crystallizer. That we are going to add into the crystallizer. So in the experiment 1, I said we used 50% seed loading. So which means the amount of seeds that we added will be equal to 11.923 grams per 750 ml of IPA multiplied by 50 by 100. So whatever the number you get, I can calculate it right now. 11.92 multiplied by 50 divided by 100. So it's around 5.96. So I added 5.96 gram of paracetamol. This is my seed mass. So you need this one to calculate QE. QE is equal to C at t equal to 0 minus concentration at any time multiplied by volume divided by mass of your seeds. So for your first experiment, the mass of your seeds will be equal to 5.96 grams. So try to calculate for experiment 2. Maybe I can calculate it. Anyway, it's simple. So for 80% seed loading, that's the only difference between experiment 1 and experiment 2. So it's the same, 11.92 multiplied by 80 by 100 m seeds. Mass of seeds in this 80% seed loading, I mean mass of seeds in the experiment 2 where we used 80% seed loading. Yeah. So this will be equal to how much? 92 multiplied by 11.92 something is not fine with my calculator. Multiplied by 80 divided by 100, or you can just multiply it by 0.8. So 9.536. So this is the mass of seeds, gram of paracetamol. So for the experiment 2, when you are going to calculate this QE value, you have to use this value. So C at time t equal to 0 minus C volume by mass of seeds, where the mass of seed will be equal to 9.536. So that's how you have to calculate T versus QE. And once you calculate this value, you have to plot this T versus QE. So this will, units will be like a gram of paracetamol per gram of seeds. Seeds are, anyway, seeds, they are also, we are seeding with the paracetamol crystals, but just for consistency, just write gram of paracetamol by gram of seeds. So you will get something like this for the experiment 1, which is a 50% seed loading, and you might get some curve like this one for the experiment with 80% seed loading. I think this is fine. I think this is more than enough, I think. And then I will quickly tell you how we did the experiment. So our working temperature is 20 degrees centigrade. Our initial concentration is 76.048 grams per 750 ml of IPA. And then our solubility concentration is something around 64.125 grams. So if this is temperature of 20 degrees centigrade, so this is your C star, is equal to 64.125. So we heat at 20 up to, I think I heated up to 50 degrees centigrade, sorry, 60 degrees centigrade, just to ensure everything is dissolved. And then I come back to 20 degrees centigrade just to check the video what I said exactly, how I did the experiment from 20 to we heat the solution from room temperature to some higher temperature, and then we came back to 20 degree very fast. So no cooling rate, like as fast as possible. And then we maintain a constant temperature at 20 degrees centigrade. And once we reach the 20 degrees centigrade, so your temperature time versus temperature profile will be something like this. Just assume this is your room temperature, and then you heat it to say like 20, say 60, sorry, something to 60 degrees centigrade, and then you cool it back to 20 degrees centigrade, and then you wait for 2 days or 48 hours. So once you reach the 20 degrees centigrade, I seeded the crystals. In the first experiment, I used 50% seeds, and then that's it. I maintained the temperature at 20 degrees centigrade, and then the crystals are going to consume your supersaturation, and then they are going to grow. So what really happens is, like, if this is your crystal, this is your supersaturated solution, the paracetamol from the solution will move to the crystal, and then it will grow. It will start to grow. So that's the principle of the crystal growth experiment. So this is what we did. And then the second experiment, we added 80% seeds. So I hope you all can follow this. So when you write the experiment, you can just mention, like, we added 76 gram, and then we added 750 ml of isopropanol solution, and then we heated the solution to 60 degrees centigrade at as fast as possible, and then we cooled the solution back to some our working temperature, and then we perform the crystal growth experiment at constant temperature, and then at 20 degrees centigrade this should give a supersaturation ratio of 1.18, and then we added once the temperature reached the working temperature, we seeded the crystallizer with some known mass of paracetamol. So in one experiment I used 50% seed, and another experiment I used 80% seed loading. So this roughly corresponds to how many grams of seeds, like for the first experiment, this should correspond to 5.96 grams of paracetamol, and for 80% seed loading, the mass of seed should correspond to 9.536 gram of paracetamol. That's how we have to write it in the report. And then we monitored the concentration using FDIR, and then we kept an eye on the particle counts and also the particle counts, the overall particle counts, and also the particle counts under three different size fractions. So using FBRM, and then time to time we check the shape of the crystals using PVM. Yeah? So that's how you have to write about the experimental part, and I think that's more than enough. So this is for your lab report. So it should so try to talk a bit about like talk about your crystallization, and then in pharma industries give some examples like where they use where they use crystallization, like put some example of okay, I read this paper on crystal growth of paracetamol, ibuprofen, and mainly they used it to purify this compound, or maybe like like curcumin, for example, curcumin, ibuprofen. There are loads and loads. Paracetamol. Paracetamol is the most studied compound in the field of crystallization. Yes, with organic crystals. Curcum, organic crystals. No, sorry. I mean, in organic compounds, the paracetamol is the most studied material. Yeah. And then, so try to talk about introduction about crystallization. It's a purification technique, why they use, where they use, which type of industries they like to use crystallization, what are the compounds that you can crystallize, put some references here and there, and don't put like a write like a 10-page report or 20-page report, and at the end just list the references. Don't do like that, because I want to know, like, if you say crystallization is amazing technique or beautiful technique or blah 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 technique, whatever you write, at the end of the day, you for each statement, not each statement, at least for some specific statement, the reference should follow your statement, so that I will know, like, you gain some knowledge from some work, and it is okay if you give the credit. It's not called plagiarism, so it is giving credit to the right people. So it should be, so pay attention to the references. So try to talk a bit about crystallization and something, and then in the introduction try to talk a bit about pat. So why pat is important, and why we have to integrate pat with crystallization, and also talk a bit about pat tools, like why we need to implement, why industries are trying to integrate all of their manufacturing units with pat, not only in the crystallization but also the other downstream operations, like and drying, and also during milling technique, and also after tableting. So there are so many reasons. So try to talk a bit about the applications of PAT in pharmaceutical industries, and then give some examples. It's very easy to find. This part is very easy to find. If you're really struggling, just put some Zlatan Nagy. He's a professor from Purdue, and Alan Myers, and he's a professor from MIT. If you just put this name, you will get their papers. So you can have a look, and then try to add some introduction about where the pat is applied and so on. And then you go to the experimental part. Try to explain how we did the crystallization experiment. I already said to you during this lecture. So try to add how we performed the crystallization experiment and so on, and then what are the pat tools we integrated, and then why. So we used FTIR, and then we talk a bit about principles of FTIR, and then principles of how the FBRM works, and then how the PVM works. So FTR is something like what we are measuring is like absorbance. We are not directly measuring the concentration. I already showed you how to convert your spectra into absorbance in the video. So try to have a look, but you don't have to write the whole procedure what you saw in the YouTube video. So that YouTube video is to keep you aware, like how to do the experiment, how to play with particles, how to communicate with the particles, and how to get the information from the particle, and how to control the particles, and how to control the reactor itself, and how to connect the information that we obtained from different spatules into one single window, which using this eye control software. And then how I don't know how to say, like how easy the data management becomes when you use all these tools and associated software that comes with it. And then how easily we converted all those results into from into we transferred all those results into one particular software, and then we just exported the whole data in no time, in less than 5 minutes. So try to talk a bit about the general advantages of this part in this section. And also try to you must give the working principles of FTIR. So what we monitor is absorbance. So this absorbance will increase with concentration. So following the Beer-Lambert's law. So, and both the compounds that we throw into the crystallizer, your paracetamol and IPA, both are IR active molecules. So which means both molecules can absorb the your isopropanol. So the rule is like this: if you have 2 paracetamol, the absorbance will be somewhere here. If you have 4 paracetamol, it will absorb more infrared, so it will be here. If you have 6, it will absorb even more IR, so it will be here. So and so on. So it goes like this. So from absorbance you can calculate the concentration. Yep. So I used yeah, how do you call, like a calibration free method which is developed by me. So I don't want to to load you with the mathematics of how to convert your absorbance units into concentration, but I already converted into concentration. So I will directly give time versus concentration, and then I will give you the data that we obtained from FBRM. So try to write the working principles of FTIR and also FBRM. FBRM is also, it won't measure the actual particle sizes. Say like it passes some let's change this. It passes some laser here, and just assume this is your particle. How to draw this? Okay, let's put a rectangle. So it will pass the light, and then it will hit, and then it will go back to the detector. So the distance traveled here, so that will be the length. For FBRM, that's the length. So FBRM don't see the actual length of the crystal. So it measures the length in terms of the distance traveled by the light, or the path distance. So imagine if the same crystal that, and then you have your laser coming down. If the same crystal comes in this direction, the same crystal, the length will be this one, will be higher. So what it measures, this length that which FBRM measures based on the distance traveled by the laser, it's called chord length. So talk about these working principles of FBRM. So okay, this is not it won't give accurately the particle size, but in front of the camera, every second we will pass in, I don't know, statistically at least, like or every minute we will we will we will measure at least roughly 100 to 200 crystals. So on average we will get the decently correct results that can mm, that can that can that can capture the information about the size fraction, and then the percentage of crystals under each size fraction. So it's a good technique. So try to write about the working principles of chord length. PVM if you know how, it's very simple technique. It works like a normal light microscope, or like it looks like a digital camera to me. So this is straightforward and simple, yeah? So try to write the working principles of FDIR, try to write the working principles of FBRM, and also the PVM. So these three things. So and then we just talk why what we are measuring using these tools, and then you go to the results. Present your results. As I said before, it should be supersaturation versus time, delta C versus time, and then your counts, particle counts versus time for both experiments. Again, NP versus time. This is for 50% seed loading, this is for 80% seed loading, and then one more graph, QE versus time. So something like that, 50% seed loading, 80% seed loading, and then try to write some. One more thing I forgot to tell. So if you look at this supersaturation, you will start from 1.18, and then you will end up when it reaches saturation point, which is 1. S is equal to 1, and we performed all this experiment at 20 degrees centigrade. So what we so what's happening is like supersaturation is decreasing with respect to time. So this type of experiment is called crystal growth, and sometime to be specific, it's called isothermal desupersaturation experiments. So that's what we did in the lab, and this experiment was assisted by Pat. So this is what we did. We did two experiments. We did two isothermal desupersaturation experiment at a constant temperature of 20 degrees centigrade, and with the initial supersaturation ratio of 1.18. So, and then you can tell to me some reason, like, so if you take this delta C versus time, so 50% curve will be like this, and then 80 percentage it will crystallize more faster, so your reaction will come to an end more faster. And the reason is simple. It's, you can just imagine, you take a crystallizer, imagine you start with a supersaturation of 1.18, same experiment 1.18, you put only one crystal, for example. So which means you are going to move some molecules to one particle in 1 minute. And just assume in 1 minute we transferred, say, two molecules to the surface, 1 and 2. So it will be like 2 molecules in 1 minute. And the same trend, just assume this time we have two particles, which mean higher seed loading. And then in 1 minute we can transfer 2 molecules per minute, 2 molecules per minute. So so that's why your growth rate will be very high at initial conditions, and then it will eventually slow down because your supersaturation is getting consumed much faster, and the kinetics will decrease after some point. So try to put this reason in the discussion part, so that's at least like how do you say, like your experimental part should be extremely strong, your working principles about your instrument should be extremely strong, introduction should be extremely strong, and then discussion part, I know you don't have expertise in the crystallization field, so try to put like say like at least two statements based on each figure, and then give some justification, this is what I think, and then just to tell why the particle counts are not changing, why they looks almost constant. Yeah. So I found, I explained a few reasons in the lab video part 2, I think part 3, I think, where I was analyzing the data, and then in part 1, I think in this lecture and also in the previous lecture, I talked a bit about why the number of particles remain constant. So it means it's a controlled crystal growth experiment. So at the end of the day, our motive is to control the crystal growth experiment. I started with some number of particles, and then I finished with exactly the same number of particles. Yeah, so that's the whole purpose of doing this experiment. Yeah, and then we can calculate. So if you remember, 50 percentage seeds, and then 80 percentage seeds. So that's a mass of let's go back, 5.96, and then 9.536 grams. We know the particle size is ranging from 180 to 200 microns, and if we assume they are spherical and the average particle size is 190 microns, from this information, like the average seed size, and then from the mass that we added in the crystallizer, and also from, if we know the shape of the paracetamol crystals, it will be something like this. From this one we can calculate exactly, not exactly, the quantitatively the number of crystals in this one and the number of crystals in this one. But anyway, for your lab report you don't need to do these calculations, but I will put some exam type problems based on, because you are not only learning everything just to solve your laboratory report, you are learning the whole crystallization process. Yeah, so in this week 3 we covered almost week 2 and week 3, we covered almost, in fact, more than the essential things that you need to know in the field of crystallization. I think if you followed all the lectures, I think you this time you would be really strong in the field of crystallization, at least the basics of crystallization, or if you want you can call fundamentals of crystallization. So we will solve one problem. That time I will show you how to convert your mass into some number. Imagine if you have 10,000 crystals. So if we go back to this graph, number of particles versus time, so this one we get from FBRM. So what does that mean? Like if you start with the 10,000 particles, you end up with 10,000 particles in the crystallizer. So this is called controlled crystallization. And why this is happening? Think a bit about your metastable zone width, solubility, metastable zone width. So we are doing at 20 degrees centigrade. So at 20 degrees centigrade, we have a supersaturation of 1.2. So this is much lesser than your metastable zone width, concentration at metastable zone width. So which means we are somewhere in this line, in this region. So if you don't understand what does this mean, watch part 1b in detail. Yeah, and once you finish your graph, and then once you talked a bit about your results, make a conclusion, decent conclusion. So something like, we performed a crystal growth experiment, we changed the seed loading, we did everything else at a similar same conditions, like constant temperature, constant agitation speed, the same initial supersaturation, and clearly seed loading increase the whole kinetics a bit faster. And then try to mention that, okay, the kinetic constant that I calculated using the kinetic expression was this number and that number, and then the initial crystallization rate was was what number, I forgot. So you can calculate initial crystallization rate. I already showed you how to do that, and I think that's more than enough. Let me check whether I showed initial crystallization rate. Okay, you don't have to calculate the initial crystallization rate. Yeah? Just ignore it. So calculate kV and then your qm value, and that's enough for your report. And try to put those values in the conclusion, and just to tell the kinetics is much faster, or the whole process is much faster when you work with a higher seed loading, which is 80% seed loading. And then try to put a feedback. What do you think about this experiment as a whole? And once you finish this one, your assignment part comes. You can call this as a like a general intro to PAT, and then list all the other PAT tools like near IR, Raman, UV, their working principles, and give 1-2 examples under each. like what they where they used in the industries. Try to find some literature, so where they used pat UV Raman near IR. Yeah, and then you try to include this one in your final report. So I don't know, the word limit for your lab report, I'm going to set it to 10,000 words in total. And don't ask me how much mark for conclusion or how much mark for your introduction. And then, oh, I forgot to mention, add abstract. Just abstract, just mention like crystal growth experiments were performed, or if you want, you can tell like isothermal desupersaturation experiment were performed at two different seed loadings and at a constant temperature of 20 degrees centigrade, and we used the we crystallized the paracetamol in isopropanol solution, and we maintained a process condition of blah blah blah, and then they we try to fit the experimental data in a second order kinetic expression, and that equation is given by q is equal to some numbers, and then like we calculated the kinetic constants, and then these are the values that we got, and then finished abstract, and then you make a conclusion. I already mentioned what you should put, and then put a reference here, reference at the end of your lab report and reference at the end of your assignment, and then include as much as figures, like working principles of UV, for example. There must be loads of images. Sorry, my handwriting is off. Include as much as figures as possible. So show the how UV looks like, how the near IR looks like, how the Raman looks like. Talk a bit about the working principles of each, and then you can put some nice figures for this one, and put some model UV spectra, how they look like, how some model Raman spectra, how they look like, some model near IR spectra, how they look like, and some case study under each. And then if you took some values from literature, then you can even copy paste the graph, like this is the graph they got using UV, that's the graph they got using near IR, and then but you must give the references. If not, it will become like a plagiarism. So give references. Yeah, and I think that's enough for this lab plus assignment. I think some of you said like I posted too many videos in this 3 weeks. In fact, if I used a PowerPoint and then if I explained you without going into the details, so this is the equation. It looks beautiful. It can do so many jobs. You will not understand. Believe me, crystallization is not an easy topic. So that's why I have to go very slowly, and I have to follow this pen and paper technique, which is not at all bad. At least at the even after you finish this course, one day you will realize that you will remember something, and that's because this module was taught in this way. So it's not a bad idea. So don't get angry on me for the reason that I'm posting too many videos. So you are not only learning about lab, you are learning completely about crystallization as a unit operation. So let it write here. We learned the crystallization unit operation. We learned all the basics. In fact, we didn't cover like different type of crystallizers. I think it's not necessary for at the moment. Yeah, so I think I'm going to stop everything related to crystallization, I mean the theory part, and probably I will solve some example problems. I need to create some problems. I'm going to create based on some experimental data that we got from our lab, and then I'm going to create my own set of problems, and then I will try to solve it for you. So we will try to solve like maybe 4 to 5 2 mark problems, and then maybe 1 4 mark problems. So that's what you are going to expect in the final exam. And I think I said everything whatever I want to say. If something is missing, if something you can't understand, please tell to me. And and, and please kindly go through the notes slowly, listen to the videos, whether you like my accent or not, or whether something I'm if I'm not explaining clearly, just call me in the teams. A few students already called me in the team, so I talked with some of them. So if you don't understand, just call me and just ask me. I think that should be enough. So thanks for listening. I think I am not going to post any more videos under the topic of crystallization. So next week we will we will go to the you have one more lab, don't forget that, super pro design. And that's not tough one, so I will solve one model exercise, and then I will give you some case study which you need to use super pro design software, and then I will tell you how to solve the problem which I'm going to give. It's not going to be really tough. So if somebody is panicking that we are week 3 or week 4 and we didn't even start the other lab, don't do. It's easy. Next week I will I think it's better I record and upload it, and then you just have a look, so that you can play one step and then pause the video, and then drag and drop the unit operation in your computer screen, and then play it again, and then draw some arrows, pause the video, and then go one by one. So that was more easier to follow than taking like a live tutorial and in 2 hours. Okay, that exercise is extremely simple. In 2 hours, if I rush through the whole exercise, nobody can follow it. I promise that. So I put it like I make the recorded videos, and then I will upload it, and then you have to do it very slowly. And so the whole idea of the second project or the second lab is to give you some idea of how the graphical user interface looks like, what are the unit operation this software contains, how you copy paste or drag and drop in your window, and how do you draw arrows, and how do you connect one unit operation with another unit operation. For example, the thing which we did now, like paracetamol crystallization followed by filtration, we can design that in SuperPro design software. It's very easy. So I will give you some this type of problems. So you and then I will tell you how to do that. And so don't panic about the second lab. You will do it in time. So keep that in the mind. And I know few of you don't have the Windows operating system. So I will talk with Barry, so you will get access to some one of the university computers, so you can access from your home, and then you can finish the project. But anyway, you are going to do that project in groups, and if you do that project in groups only, then you can finish it in time. So it's not like a warning note, it is simple, but it's better to work in groups. For few things it's better you will learn even more when you work as a group. So that way we will meet the expected learning outcome. So I think I talked a lot. I will stop now. Thanks for listening to me.